All right, Chapter 9, Worksheet problem number 2. We're given an element representing our state of stress at a point, and we need to find the principal stresses and the maximum in-plane shear stress and the average normal stress at the point. And then specify the orientation of the element in each case. So, in summary, part A, our principal stresses are sigma 1 and sigma 2, and then their orientations are theta P1, theta P2. Part B, we're finding our max in-plane shear stress, and then the average normal stress, that will be on each face. And then our theta S1 and theta S2 are the orientation for that element. All right, we're given our sigma x, sigma y, and tau xy over here. Sigma x is tensile, positive 45. Sigma y is compressive, so negative 60. And tau xy is a positive 30 because it's up here on this positive x face going in the positive y direction, positive 30. All right, so our solution, we simply just need to plug everything into the equations that we derived in the Chapter 9b lecture. So we're going to use our derived stress transformation equations to find our principal stresses and max in-plane shear and their associated angles. Pretty straightforward. Right? So you just have to plug the numbers into the equations and know that sigma 1 is greater than sigma 2. Sigma 1 is our maximum, sigma 2 is our minimum normal stress at our point. So you have a positive 53 megapascals for sigma 1 and a negative 68 megapascals for sigma 2. The angle at which they're going to occur is coming from this equation. Tangent of 2 theta p equals tau xy over sigma x minus sigma y over 2. Plug in our 30, and sigma x minus sigma y over 2 is 52.5. Since both of these values are positive, that means our inverse tangent of 2 theta p is going to be in the first and third quadrants, because that's where we have a positive tangent for this 2 theta p. So what we end up getting is 2 theta p equals 29.74 degrees. Divide that by 2, and theta P1 is 14.87 degrees. We know that this is theta P1 because we can plug this into our stress transformation equation, and when we do that, we're going to get 53 megapascals. Then our theta P2 is either going to be plus or minus 90 degrees from that, because we know that that's our angle from the x to our y-axis, or from our x prime to our x double prime axis, as some places refer to it as. We just typically use an angle that's between negative 90 and 90 from there. So we're going to subtract 90, and theta P2 then is negative 75.13 degrees. If you plug this value into your stress transformation equation for sigma x prime, you'll get negative 68 megapascals. So you can always check these answers against each other. That's an important thing to do, not just for this homework, but for your next homework and on your quizzes and exams. So when you draw your element for principal stresses, remember all you have is normal stresses. Okay, when you have maximum normal stress, you have 0 shear stress, so no shear. And then our angle to theta P1 from our original x-axis, sigma 1, that's a tensile stress, so it's going away from the element. And you can just label it with sigma 1, or you could write 53 megapascals there. And then the angle from the x-axis to sigma 2, it's theta P2, and sigma 2 is compressive, so draw the arrow toward the element and label it sigma 2. Or you can label it as a positive 68 megapascals with the proper direction of the arrow. Okay, so that's for part A for your principal stresses. Now for part B, your max in-plane shear, you just have this equation, which again is our radical under here. And so that value is 60.5 megapascals. And since it's plus or minus here, typically all we care about is our absolute value here, which is our maximum positive shear stress, so you can just report it like this. And then you have to decide on which face is it going to be a positive shear stress and which face is it going to be a negative shear stress. And you can figure that out from your theta S equation. So to find the angle at which theta s occurs, mentioned before in the slides that all we have to do is add or subtract 45 degrees from our principal angles, or we can use this equation, which is just the reciprocal of our principal angle or principal plane equation with the negative sign. And so you get tangent of 2 theta of s is negative 52.5 over 30. This means it has to be in either the second or fourth quadrant, because one of these values is negative. And we get theta s1 is negative 30.1 and theta s2 is 59.9. We'll see when we do Moore's circle though, really we can just use this. Theta s1 is equal to theta p1 minus 45 always, and then theta s2 is theta p1 plus 45 degrees. And that's always the case. Then when you draw your element, you have your max in plane shear on every face. And when we rotate theta s1 down here clockwise 30.1 degrees, we have a positive max in plane shear. So it's going to be going in the positive y direction or positive y prime direction. And then so on the opposite face, it's going to be going down. And then the other shear stresses have to meet in the two corners. So once we establish one direction, we can find the other three directions just based off of it. And then your average normal stress, don't forget, is going to be acting on each face. And sigma x plus sigma y over 2 is our average normal stress. You get a negative 7.5 megapascals. So be sure to label that on each face. That's compressive, so draw the arrows toward the element and just label it sigma average. All right, that's it for this problem. You should be good with all of the problems on your homework. So once finished that, go ahead and take a look at the Moore's circle lecture slides.